and thanks for doing it now. But all right, I guess from next time I can be more careful what else can be done.
Sir, can you share these notes as well because the recording won't be there?
No. Again, these notes are a continuation of the previous one, and this thing again, if somebody wants, like this is just like one small section from the book. You can go and read also, and if somebody has any doubt, I can maybe repeat it or ask these things. This is not much. This is just one small lecture, and I don't have it separately. I might make a separate note and send it, or I can give you some reference material for it. But again, these things I do very informally, and this is not proper notes. So for that reason, I won't be sharing these notes. So yeah, that's about this thing. And those who are attending can maybe help out their friends also. So what we have covered till now, just to repeat, so that those who are accessing the recording can do it. So what we did till now was we started with the applications of BFS and DFS, and we started with the first thing we discussed was that we can get all connected components in order m plus n time, and the second thing was that we can recognize that a graph is bipartite in order m plus n time, and that's what we are doing right now. And I had forgotten recording, so sorry about that. So what we did, we first described an algorithm. What the algorithm did was look at one vertex. Okay, so let me just, so that those who want to see can see it also. It won't take too much time. So we first went through this. Okay, yeah. So we went through applications of BFS and DFS. So we were looking at finding the set of all connected components, and we saw that we can start from a vertex that is not visited till now and do the BFS starting from there. And then we did a running time analysis for that, and we figured out that the total time taken was still order m plus n. Then we came to bipartite graph. We gave three definitions of bipartite graph. One is the partition definition, that you can divide the vertex set into two such that both the parts are independent. Then the second definition was you can color the graph with two colors. You must have seen that before. And the third definition was that a graph is bipartite if it does not contain any odd cycles. All the three definitions are equivalent. This was given as an exercise. And then the question was testing bipartiteness. And for testing bipartiteness, we came up with an algorithm that, okay, we start with a vertex and look at all its neighbors. We want to give it color, the other color. Then we want to look at their neighbors. We want to give it some other color and so on. This is what we want to continue doing. Then we started with BFS. And we said that, okay, all the vertices in some layer will get, in L0 will get color 1, in L1 will get color 2, in L2 will get color 1, and so on. So all the even layers would get color 0, would get color 1, and the odd layers will get color 2. And now we are trying to show that this procedure, so first we argued that this procedure runs in order m plus n time, because the extra work we were doing was not much. We just assigned the vertices the colors while putting them in layers, and in the end we just looked at all the edges and saw that they were given, the endpoints were given different colors, and that required extra just order m time in the end. And in between whatever we were doing, we were assigning the colors to the vertices by keeping an array color, and that takes extra order n time. And now we are arguing the correctness. So for the correctness, what we are saying, we are showing a lemma that if G is a connected graph, and if the layers are L0, L1 to Lk, then either there is no edge among the nodes of the same layer for all the layers, and then the graph is bipartite, and then the procedure correctly outputs a two coloring of G, right? Or the second case is there is an edge between vertices of same layer, and the graph is not bipartite. Okay, so And if this lemma is correct, if we can prove this lemma, then the above procedure outputs correctly. Because if the graph is bipartite, then like case 1 holds, and if the graph is not bipartite, then case 2 holds, and then two vertices of the same layer will have an edge between them, so they will have the same color. The algorithm will output no. So what is the proof of this lemma? So let's say case 1 first. So can anyone, like, it's not very hard, but let's just try to come up with a proof.
In case one, it is a two coloring is already produced, and we can say that it is correct because there are no edges between the same color. Because in between like two layers of BFS, there can only be an edge if the difference of layers is one.
Exactly. So if so who said this? Amit, you said, or Manish? Who said this?
So I did.
Amit. Okay, good. So yeah. So if there are no edges among vertices of same layer, then due to property of BFS, there can only be edges among vertices of adjacent layers which have different colors. From the algorithm, okay? So we got a proper two coloring of G, and by definition 2, G is bipartite. And yeah, please from next class, like try to remind me in case I forget recording, okay? Thanks for reminding now, like, it's better than not recording at all. Okay, good. So what is case 2?
Sir, we can
Sir,
prove by induction.
Yeah. Say?
Sir, first we set the color of the first layer L0
Yes.
as something,
Yes.
and then we can prove by induction that for every layer Li plus 1, all the colors of that layer, the vertices of that layer will be the opposite of the colors of layer Li. So L2, L1 will have the color 2 because there is an edge between every element of L1 and every element of L0, and this we can prove by induction for all the layers.
Yes, but then you are talking about, like, there is some thing you have to, like, this is correct, but there is some things you have to be careful about. One is that you are talking about giving L0. So first you have to start with without loss of generality, that you are giving L0 color 1, that inverting the color does not change bipartiteness, and then you can show by induction you are right. But a more direct way, anybody?
so that if there is a edge between the same layers, then we
Yes.
can generate a odd cycle.
Exactly. So what we had seen a lemma when we were doing BFS, that what is the layer Li, set of vertices in G at distance I from S, right? We have shown this lemma that, this can be shown. I just wrote the statement of the lemma. It can be shown by induction. I might have given it as an exercise. So for all the vertices in Li, what is the distance from S? It is I. So suppose Li is the layer where we have the edge. So now you have S, and this is Li, and there are two vertices U and V. So let U, V belong to Li such that UV is an H. Okay. So that means there is a path so this length of path is I, this length of this path is I, and this is 1. So that means we get a cycle of length 2I plus 1, right, in G, which is S to U to V, where these are to S. Length I path. This is length 1. And this is length I again. Right? And then by definition 3, G is not bipartite.
Sir, here the path from S to U and S to V does not have to be disjoint, right?
Yes. The path from S to U and S to V does not have to be disjoint. That's a good point. So what do we do then?
So we can just say that they have a common ancestor in a same layer.
True. So thanks for pointing this out. It's a good nuance that you. So what Amit is saying that maybe the path from S to U and S to V is not disjoint. So So this is the case. So case 1, if the paths are disjoint. Okay. And what is case 2? There exists a common ancestor of U and V in the BFS.
So we can include case 1 and case 2 as well. Like
Yeah, I mean, common ancestor can be S
for
itself.
the S, yeah.
Of correct. I mean, sake of simplicity, since I initially did the case assuming that from S the paths were disjoint. Of course, these cases can be combined. So there exists a common ancestor. So basically, what you can show is that there exists a common ancestor. Either S is a common ancestor, or in the BFS tree, you have a vertex from where the paths diverge. So let whatever W be the common ancestor, and then again the same proof works because W is in layer whatever Lj, let's say. Then what you get is the path of length I minus j 2 times plus 1, which is again, cycle of length, which is again odd. And again, you showed that by definition 3, G is not bipartite. Okay. So, and about this common ancestor, just like, so case 2, I just wrote that there exists a common ancestor, but how do you show that there exists a common ancestor? Like, if you want to, I just want to, like, drill a bit more preciseness into it, drill a bit more precision into it. So, how do you show that there exists a common ancestor? If S is not there, then how do we say that there exists some other common ancestor?
So can you repeat the question?
So why there has to be a common ancestor apart from S? So case 1, so if I wanted to say, if I wanted to show that there exists a common ancestor of U and V in the BFS tree, how do I show that? I want a proof of that.
You can trace back from
Sir,
that
S
path.
is always a common ancestor because they'll all go back to S eventually.
Exactly, S is always a common ancestor, and okay, so there exists a common ancestor of U and V in the BFS tree, so that is not like we want the lowest common ancestor.
Yes, sir.
Yeah, so that we want to be W. So this is what I want to
So we can show that all the elements that are common in the paths, they occur in a particular order. Like if X and Y are common in the paths from S to U and S to V, then
So basically, look at what can be the thing that look at the path from S to U and S to V, and look at the common section of the path. Look at the last vertex that is common in the paths. Okay, so either S is common. If S is the last vertex, then S is the lowest common ancestor, and if S is not, then the last vertex that is common is the lowest common ancestor, right? Or least common ancestor, as it's called. Okay, so there are some details that you would want to figure out that okay, that is what, since W is the lowest common ancestor, that is why we can say that these paths are disjoint. If it was not the least common ancestor, if it was any common ancestor, then we cannot say that these paths are disjoint, for example, right? Okay, any questions? No? Okay, so this was the proof of correctness of the algorithm, that whatever we outputted was actually right, that we actually get the correct answer from the algorithm, that if the graph is bipartite, then the algorithm correctly outputs that it is bipartite. In fact, it also produces a two-coloring of the graph. And if the algorithm says it is not bipartite, that means there are two vertices in the same layer which have an edge, or they have been given the same color by the algorithm, and then the algorithm says no, then actually the graph is not bipartite because we have produced an odd cycle in that case. Okay. Cool. So if there's no questions, take 1 minute more or like 30 seconds more if you have any. Okay, so tomorrow there is no class from an email that was there. So we'll instead we are having the Friday schedule on Saturday. So the class will be on Saturday on 11 a.m. Okay. So see you on Saturday then.
Okay, sir. Thank you.
Thank you.
Thank you, sir.